Hello, I am Yi from University of Chicago. First, I would like to acknowledge my co-authors, Dr. Prasanna Balaprakash and my advisor, Professor Yanjing Li. I'm going to present FIdelity, Efficient Resilience Analysis Framework for Deep Learning Accelerators. Here is the key message of this video. Resilience analysis is a top priority for deep learning accelerators, but previous studies have many limitations. Therefore, we present our resilience analysis framework called FIdelity, which is both fast and accurate and does not require the access to RTL. The key idea of FIdelity is to leverage unique architectural properties of deep learning accelerators. We developed an algorithm that requires only minimum amount of hardware information without the need to access RTL code and can capture accurate error behaviors in software. Deep learning accelerators have been used in a wide variety of application domains, and we all depend on them. Some of them are even safety-critical applications that demand high resilience. For example, self-driving cars, medical analysis, and industrial applications working in extreme conditions. For the other applications, even though they might be more tolerant to errors, but they still have resilience requirements or standards that must be met. For all the deep learning accelerators, hardware errors are a major concern. One prominent example are transient errors that occur in the logic portion of a design, which we call logic transient errors. Some examples of these errors include soft errors and dynamic variations. Soft errors are radiation-induced transient errors caused by neutrons from cosmic rays and alpha particles from packaging materials. Dynamic variations are those errors caused by changes appear during circuit runtime. The changes, for example, can be voltage droops or temperature fluctuations. Even though these transient errors can also affect memory, and memory errors have been the focus of previous work, it turns out that when these errors affect the logic portion, they will bring severe consequences. Here we give an example of NVIDIA-A, NVIDIA's open-source deep learning accelerators. If NVIDIA-A is used for self-driving cars, then the industrial standard only allows its logic portion to have a fit rate smaller than 0.2, where the fit rate is a standard resilience metric. However, our research showed that the actual fit rate for NVIDIA-A's logic portion can be higher than 9.5. It means that resilience requirements cannot be met if the logic portion of deep learning accelerators are left unprotected. So obviously, for safety-critical applications, meeting resilience requirement is important, but even for other applications, as we have discussed, they cannot tolerate an arbitrary amount of errors. So resilience analysis is essential for all applications to ensure safety standards and resilience requirements are met. In addition, resilience analysis can be used to assess the impact of fault attacks to enable architectural explorations for optimal trade-offs between performance, power, and reliability. It can also be used to quantitatively compare different designs for benchmarking purposes. Overall, due to its top priority, resilience analysis should happen at the very beginning of the hardware design phase. It cannot be just an afterthought. Resilience should be guaranteed from the very beginning of hardware design. So how do people perform resilience analysis? In general, there are two types of methods: hardware RTL fault injection and software fault injection. Hardware fault injection techniques are accurate, however, RTL simulation is slow. Moreover, the need to access RTL means that the analysis cannot start at the beginning of hardware design phase, because RTL is not likely to be ready that early. Meanwhile, software fault injection techniques are fast and do not require RTL, but they are highly inaccurate. The reason why software fault injections are inaccurate is that simplistic software fault injection model hardware errors as single-cycle bit flips in a single architectural state. However, the actual hardware error could lead to many different possibilities. For example, one hardware error can cause single or multiple bit flips in one or more architectural states. It can also cause other system-level anomalies, such as system timeout. In order to show simplistic software fault models fail to capture the actual hardware error behaviors, again we use NVIDIA-A as an example. Here is just a very small portion of the weight data path. As we can see, the weight data path fetches a weight value from on-chip memory and dispatches it to compute units or MACs. NVIDIA-A has 16 MAC units computing 16 consecutive output channels in parallel. Each weight value is only sent to one MAC unit. For every MAC unit, the weight values are reused for 16 clock cycles to compute 16 consecutive neurons belonging to one channel. In this example, the weight data paths fetch a weight value from on-chip memory. When the value propagates to this flip-flop, a transient error happens. Now the value is incorrect. The value then propagates all the way to this MAC unit, affecting one neuron output. Since there exists a loop in fault propagation, this faulty value is reused for 16 clock cycles, which makes it affect 16 output neurons belonging to the same channel. However, in a simplistic software fault model, one error can only be modeled as one bit flip in one weight value or one bit flip in one output neuron. Neither case would accurately model the true hardware error behavior. In summary, we have seen the weaknesses of general software and hardware techniques. Previously, there do exist some studies that specifically target deep learning accelerators. However, they focus on memory error only. Remember, the errors occur in the logic portion is a major concern. The question here becomes how to efficiently perform resilience analysis on the logic portion of deep learning accelerators. The answer is our FIdelity framework. FIdelity is capable of analyzing transient errors in both logic portion and memory. It is applicable to a wide variety of deep learning accelerators. It inherits the strength of both software and hardware techniques, but overcomes all of their limitations. It is fast, it is accurate, and it does not require the access to RTL. So how exactly do we do this? We find that there are special architectural properties of deep learning accelerators that we can leverage. The first architectural property is that one error can only directly affect the output neurons of the current layer. This means that our framework can first determine the error effects in the current layer, which is the locations and values of the faulty output neurons. Then after that, we perform software fault injections to those faulty neurons, change their values based on our analysis, to make the error further propagate to the network output. So it's clear that step 1 is very important. But how do we determine the error effects in the current layer? We turn to the second architectural property, which is that one hardware error affects the deterministic set of output neurons in the current layer, due to the regular structure and well-defined data flow and reuse algorithm. Therefore, we create an algorithm called reuse factor analysis. The input of reuse factor analysis is a minimum amount of hardware information, which does not require the access to RTL. By performing reuse factor analysis, we are able to obtain accurate software fault models for later accurate software fault injections. So, what is the minimum hardware information required? To understand this, let me first introduce the fault model and definition. The abstraction of one logic transient error is a single cycle bit flip in one flip-flop, and we define the target flip-flop to be the flip-flop we need to perform reuse factor analysis on. So the majority of the information we need are related to the target flip-flop, which include the following. Does the target flip-flop have a feedback loop? How many MACs are connected to the target flip-flop? How long is the one cycle value of the target flip-flop used by MACs? In addition to target flip-flop information, we also need to know which output neurons are computed by each MAC. Notice that all of these informations here can be obtained from high-level hardware diagram or descriptions. They can even be estimated from design plans and varied for sensitivity analysis. This is very beneficial because resilience analysis cannot be an afterthought. At the early design stage, RTL might not be available yet, but we still want to understand the resilience property. And even if RTL is available, RTL simulation is very slow, and RTL code might be confidential between separate design teams. By using the FIdelity framework, we provide a method for efficient resilience analysis using minimum amount of information. So given these input, what does reuse factor analysis do? Here we show a skeleton of our reuse factor analysis algorithm, which are formed by a series of for loops. Some of the loops capture flip-flop to MAC relationships. Notice here we capture both the temporal factor and the spatial factor of the flip-flop to MAC relations. The temporal factor accounts for the case where one flip-flop value is reused by one MAC for multiple clock cycles. The spatial factor accounts for the case where one flip-flop value is used by many MAC units in parallel. Reuse factor analysis also captures MAC to output neuron relationships. So by walking through these loops, reuse factor analysis connects flip-flop to MAC unit relationships with MAC unit to output neuron relationships. Therefore, it creates a connection from bit flips and flip-flops directly to the position of faulty output neurons. To show you how reuse vector analysis works, we revisit NVDOA's weight data path example that we showed earlier in the video. Recall that an error in this particular target flip-flop affects 16 consecutive output neurons, since the weight value in NVDOA is reused 16 times for this MAC unit. Given this target flip-flop, even if the logic in the entire data path might be very complex, reuse vector analysis only needs a minimum amount of hardware information, which we are shown in previous slide. And we don't need to know the detailed hardware diagram or RTL at all. So what do we need to know? We need to know that the target flip-flop does not have a self-loop. We need to know the target flip-flop only connects to MAC 1. A one-cycle target flip-flop value is reused 16 times along the data path, and the output neurons computed by MAC 1 belong to the same channel and their indexes grow in row major order. We can directly apply this information to reuse vector analysis. By iterating these loops, the positions of faulty neurons affected by an error in the target flip-flop can be determined. And here we can see that the positions of faulty neurons obtained from reuse vector analysis exactly match the actual hardware error effects. After deciding the positions of faulty neurons, how do we determine their value changes? We then leverage the third architectural property of deep learning accelerators. Data path flip-flops closely match software variables, such that one bit flip in target flip-flop can always find a set of equivalent bit flips in software framework, and the software framework will use these bit flips to decide the faulty neuron value changes. To analyze the entire system, we need to come up with accurate software fault models for every single flip-flop. However, due to the number of flip-flops in the system, modeling every one of them requires very detailed hardware information, which might not be ready or might not be accessible. How do we make it a tractable problem? We leverage the fourth architectural property of deep learning accelerators. Data path flip-flops in the same pipeline stage and belonging to the same variable type have the same error effects, such that we can group flip-flops into categories. Resilience analysis only need to be performed to each flip-flop category. If we know the rough percentage of each category, then we know the overall resilience of the accelerator. We apply FIdelity framework to NVDOA and have provided a complete set of software fault models and flip-flop category percentages for all flip-flops in NVDOA. Our case study covers not only all data path, but also control flip-flops as well. All the details of NVDOA case study, including the exact software fault models and different flip-flop categories, are summarized in the paper. We also show how reuse vector analysis can be applied to other accelerators and articulate the correctness of the algorithm in the paper. We fully validate our FIdelity framework by performing 60K RTL fault injections on various DN workloads. We compare the RTL fault injection results with FIdelity software fault models. For data path flip-flops, our fault models completely match the RTL fault injection behaviors. For control flip-flops, we also model them accurately. After validating our FIdelity framework, we performed the first large-scale resilience analysis using NVDOA as a case study. We modified TensorFlow to support software fault injections to our software fault models. Our analysis includes a total number of 46 million fault injections covering a wide variety of deep learning applications, including image classification, object detection, and language translation. We get many different and interesting results from the resilience study. Here are some selected results. The first one we're showing here is the total soft error fit rate for the logic portion of NVDOA, which is the yellow box. We also break down the total fit rate into data path, local control, and global controls, such that we can see their contribution to the overall error effects. Notice that in our fault model, we divide control flip-flops into global control and local control. Local controls are closely coupled with specific data path flip-flops. A hardware error in local controls will only affect these specific data path. However, a hardware error in global controls in general will affect a large number of output neurons. We compare our fit rate results with the self-driving car standard. We can see that the total fit rate of these applications are around 10 to 20. However, the safety standard mandates the fit rate to be less than 0.2. Therefore, our resilience quantitatively show that resilience protection in the logic portion of deep learning accelerators is essential. We have also found that for some networks, global controls contribute to a large portion of the total fit rate. So what if we only protect the global control flip-flops, which is generally a relatively small percentage of all flip-flops? So here we show the soft error fit rate for all applications assuming the global control flip-flops are protected. So now, only data path and local control flip-flops are left unprotected. Even though the fit rate of some applications becomes smaller, they still cannot meet the resilience requirement of self-driving cars. We also have other interesting results and architectural insights. For example, we show the impact of different resilience metrics and different data precision. We also observe that faulty output neurons with big positive value changes are way more likely to cause system failures, which can inspire new resilience techniques. All the results and the details are in the paper. To conclude, in this video we present FIdelity, our new resilience analysis framework for deep learning accelerators. FIdelity targets both memory and logic transient errors. It can be as fast as software fault injection while achieving comparable accuracy to hardware RTL fault injection. Moreover, it enables resilience analysis from the early design phase when the RTL is not available. Using FIdelity, we performed the first large-scale resilience study on logic transient errors in deep learning accelerators, which reveals new resilience knowledge and architectural insights. We have open-sourced our framework. We hope that this would inspire further resilience studies and techniques. Thank you.